This video is an overview of some questions that were shared leading up to our first midterm exam, uh, looking at topics from 5G through 5I. Provided information for the exams shown here for this portion of the textbook. If it's going to be provided, I think it's going to be very valuable for you to think about each of the different pieces of information. Can you explain each of the different expressions? When would it be used? How is it going to be used? If it's provided, good chance that you're going to have an opportunity or a need to use it. I'm looking through the different questions. This first one here, writing the reaction quotient expression Q for the reaction and connecting it to the Gibbs free energy. So we have a way to be able to write a K expression and to be able to think about that in the same format when we're looking at it for the Q expression, the reaction quotient. You see that they're identical. Difference, the K is referring to when the composition is at equilibrium, and it Q's at any other time. So as I look at this particular question, I see that I have a liquid, pure liquid within here that is not going to be in my final expression. If I look at the other ones, I see a combination of gases and aqueous species. If I'm looking at the K expressed using the concentration, that's not going to bother me at all. I can look at mole amounts for each of them, and I can consider the volume that they're in. So for all of these, even though it's a combination of gases and aqueous species, I can still think about it in terms of this Kc expression. When I'm trying to connect it to the standard Gibbs free energy, given the data that I would have for the standard Gibbs free energy, I could use that to come up and solve for what the K expression is. So I would need to have that information provided, and with that come up with what that K expression is. Within my conversion within here, this would be the gas constant value that I would use for R. And once I have that, I can make a comparison between the Q and K amounts and determine the direction of the reaction or whether I'm at equilibrium. So make sure you're able to finish that part off. What does a comparison of Q and K tell you? And how would you use that information? Second one, we're looking at the scenario of the wick of a candle's lit. It burns. We have the wax melting. Is this an example of chemical equilibrium? Explain your reasoning. I think as this is taking place, I have a physical change with the candle itself melting, but I have a reaction that's taking place, a combustion reaction that's taking place. This is my effort to revisit this topic that Atkins has raised about, well, if you have a chemical reaction taking place, does that mean that you have a dynamic equilibrium? If you recall a dynamic equilibrium, if we're going to have both a forward and a reverse rate of the reaction equal, we can't have matter leaving our reaction. We can't have an open system. We have to have a closed system so that we're not losing particles along the way. So in this case, in both of these cases, I would say these are examples of chemical reactions, but because they're open systems, they're not at equilibrium. Scenario, reactions initiated. How do we make sense of our different terms? So within this one, I think a strong response would be explaining what the different symbols represent. If the reaction's progressing, if it's changing, if it's moving towards equilibrium, then the Gibbs free energy for the reaction is not zero given that composition. The Gibbs free energy change that we have for that composition for the reaction is going to depend on the value that would correspond to the standard amounts and how that is being changed by the composition that is present, and that's what Q is describing. So as the reaction is taking place, I think the composition is changing, Q is changing, and that's leading to a change in the Gibbs free energy for the reaction. What's constant within this would be the tabulated value, the one that we look up for the standard conditions, the delta G naught. Delta G naught, that's what is related here to the values that we have that we can use to come up with the equilibrium concentration, the equilibrium composition. And when I say it comes up with that, if we set the delta G for the reaction at 0, that's describing the equilibrium conditions. Under those conditions, then Q is equal to K, and that's what it means to take the delta G naught, slide it over here to the left-hand side of the expression, and under those set of conditions, we can solve for what that K value would be. So as this reaction is progressing, I'm thinking that we have 2 of the terms that we're changing and 2 of the terms that were remaining constant. This one we're asked to use information to determine K for a particular reaction. If I look within this one, I'm going to think that I can manipulate any of the reactions that I have, and that would change the equilibrium constant. How would I manipulate them? I want to make it so that when I add together the expression, it reaches my targeted one. So I think I can do that by taking this first expression, cut all the coefficients in half, second expression, all the coefficients in half, and same thing with the third. So for each of these, I've taken all of the different K values, reduced the coefficients by 1/2, and that means I take a square root for each of the different equilibrium constants. The overall K expression then would be the product of each of the ones that I am combining. So I pointed out that this is somewhat like Hess's law in that we're combining different provided pieces of information, different reactants, seeing how we change that reaction and what does it do to the corresponding equilibrium constant. But in several respects, the rules of this, they're different than Hess's law, right? We do something different when we change the coefficients. When we add them together to come up with the overall expression, we're once again doing something different. So we want to be familiar with how we can manipulate data like this and how we use it to get a K expression. Scenario here. So we're taking solid calcium carbonate, put it into a rigid container. I see what the volume is. It reaches a particular temperature, and we're going to be calculating the equilibrium conditions within that, Kc. So I think it's helpful. I'm going to start with writing what the reaction describes. I'm going to make sure, okay, it's balanced with coefficients of 1 throughout. Within this, I have a solid, another solid. The activity for those is going to be uninteresting. It's just going to have a value of 1. But I'll see within my equilibrium expression, the quantity for the gas is going to be relevant. And when I say the quantity for the gas, a K value is given here. And when Atkins just has a straight K value, that's referring to the pressure. And we want to be able to convert that from a K value to a Kc. Now, we have an equation that we can use for that. Delta N here, that's looking at products minus reactants for the moles of gas that we have within our balanced equation. And we only have one species contributing to moles of gas here. Last thought that we want to be careful with. We use bar as our units of pressure throughout here when we're using activity. And so the units of pressure are always in terms of bar when we're thinking about it in this K expression. And so because of that, when we're doing any conversions, we need to use the R value that also includes units involving bar for the pressure. So just pointing out, we have 3 different R values that are being provided. If we're using one that states that it's using bar, or that we have to know it was using bar, then we have to use this particular value here. How about this one? Does this reaction progress diagram describe a reaction with a large or small K value? What would be your reasoning? And then what if we changed it to a different K value? So as I look at this, a spontaneous change is going from a high Gibbs free energy to a low Gibbs free energy. It's moving towards the minimum. So I would say when it reaches equilibrium, it's primarily reactants. So if I'm looking within my expression here, if it's mainly reactants, that means it's a small K. Got a larger value here that would have been in the denominator. If I'm thinking for a value near 1, I'm thinking that that would say that I have, within my composition, a more even mix for when I have products minus reactants, when I look at it within the resulting K expression. And so I would draw a picture that might be more along these lines. Within this one, we're looking to do a calculation. When I'm looking to do a calculation, I want to make sure I have a balanced expression. This one's balanced with coefficients of 1 throughout. I want to look carefully here and see what is the how is the K value being described, and it's going to be in terms of Kc. As soon as I see the Kc, the concentration part, I want to be thinking about, well, what volume do I have? Because when I do Kc, I'm doing molarity, moles per liter. So I know that I can have my Kc expression here involving molarity throughout. I've got an ice table that I'm going to use, and I'm going to be using moles per liter, but I had 10 liters for the volume. So if I look and I set the whole thing up, each of these 1 mole in 10 liters is a 0.1 molar solution. So I see what I initially had. No products initially there, how it changed, consistent with the coefficients, and then my equilibrium expression. All of that algebraic terms I could then put into my Kc expression. Now in this case, notice it doesn't give us the Kc expression. That's what we're solving for. So we're going to use something that gives us some insight to the equilibrium line. So we had 0.665 moles of CO2 in the 10 liters. So this would be its concentration for the molarity. Great. I now have an X value, and I can use that X value throughout my equilibrium line and put those values all into my Kc expression. Another calculation here. So we have a equilibrium reaction. I see a Kc value listed. If I look at these, if I have a Kc, first thing I'm going to look is to say, all right, how do I have information about moles and the volume? So the volume is in 2.5 liters, and it's a sample of NH3, which is given as 21.12 grams. So if I'm setting this up, I'm going to set up the ice table. I want to make sure I'm using molarity. We would make and use the assumption that X is going to be small compared to the initial amounts. That would be my plan. And if the assumption is not valid, my objective for you on the exam, I want you to describe why it's not valid and show what the full equation would be that you would calculate. Let me show you what I mean. So within here, this would be my initial setup. I've converted the 21.12 grams of NH3 into moles, expressed it as moles per liter, and this would be my initial amount. This would be the Kc expression that I would end up using. It's going to change by 2x, x, and 3x. This would be then my equilibrium line. If I take all of those and put it into my Kc, this would be the entire expression, including all of the x terms. I'm going to try the assumption that I can neglect the x that's being subtracted. And when I do that, when I solve for the x value, it leads to something that I absolutely cannot neglect. I wanted to say that 0.496 minus an x value was really a case where it really wasn't changing the 0.496 very much. But I see that I've got a huge value here, okay? So there's no way that that's going to be possible relative to the 0.496. So I think that the best expression here would have been to say, what I would be expecting would be, if you list this, explain why the approximation that x was not, could be neglected was not valid. This is what I'd be looking for. Because it shows me that you've worked it through with an ice table, you've considered the assumption, and that this is what you would then solve. Couple here with describing Le Chatelier about how it's a useful shortcut and to think through some of the details. So within this scenario, we have an initial equilibrium reached with these particular reactants and products, and it's in a setup here where we have a movable piston. So if we add some argon gas here, if it's at constant pressure and temperature, that's going to cause the piston to move outward in order to keep the same total pressure. Argon has led to an increase in the volume. The total pressure that I have has remained the same. And in order to remain the same, I had to have an increase in the volume. Now, the partial pressure for my different components there, the CO, the H2, the methanol here, All of those partial pressures are now smaller than they were initially. I haven't changed the number of moles of those, the particles that were involved, but I've increased the volume. Their pressures have gone down, their concentrations have gone down. So as I've changed all of those, Q and K are no longer equal to each other because the moles of gas that I have when I'm considering reactants and products are not the same within this expression. There's going to be, as the pressures have gone down, there's going to be a shift within here towards the reactant side. If I were to consider why that happened, I think the fact that I'm now in a larger volume, the entropy increased for all of these gases, but it increased more for the reactants because I have more moles of gas that had their entropy increased there. And we know the direction of a spontaneous change is from a higher to a lower entropy value. That's what it means when we now have this shifting taking place. So we need to be careful. We had something that was changing the volume. That something, argon, wasn't listed within our balanced equation, but because our friend the piston was involved, we saw a change that we then had to account for, and Q and K were no longer equal to each other. Here's another one where we're looking at a particular change. So we're going to be looking at a graph here, making a sketch where we have time as reaction takes place and concentration here vertically. So initially, we only have N2O4. So I have N2O4 initially added. Its concentration will diminish, and the concentration of the product that's listed here will increase. So the NO2 initially started at 0, and it's going up. Couple features that I have here within my drawing. We see how the rate of change is more dramatic at the start, and then they level off as we reach equilibrium. That's one feature. Second feature is the manner in which it's changed. The NO2 was changing twice as much as the N2O4. So if I look for how high this one has gone up versus how low this one has gone down, that's consistent with the coefficients here within the balanced equation based on the stoichiometry. So that I tried to add that feature in as well. And then the third spot is the Kc value is said to be much greater than 1. So I wanted to make it so that these equilibrium amounts, the composition has much greater for the products than it did for the reactants. So this would be my first setup as I've reached equilibrium before I make the change. Now the change that I'm now going to make, the volume's decreased. I'm going to squeeze it in, and I tried to say, okay, I'm going to double all of the concentrations there. Now they're starting out at different spots. So if I were to double the height of this red line versus double the height of the blue one here, I see that they're doubling the concentration leads to a larger total change here for the NO2. Okay. Now, if it's now going to shift from here to reach equilibrium, I'm going to see that the NO2 is going to diminish and that the N2O4 is going to increase. When I did this compression right here, Q and K were no longer equal to each other. I'm going to see a shift in the response where the NO2 is going to diminish and the N2O4 is going to increase. Again, I tried to make it where the change was more dramatic at the start and then leveled off. And I tried to make it, again, consistent with the coefficients. It's changing twice as much for the NO2 as it is for the N2O4, or approximately. And I see that, the final concentration that I get with the NO2, there's been a shifting, but it's higher than where I had that initial equilibrium. Because after all, the volume that it's now in is smaller. Another Le Chatelet one, this observation concerning an endothermic reaction and a change in temperature. What would Le Chatelet predict, and how does thermodynamics play a role? So Le Chatelet would say if it's an endothermic process, raising the temperature is going to favor the products. This is leading to a change in the equilibrium constant, a change in the K value. You make the change, Q and K are no longer equal, so we see a shifting that then takes place. There's a few different ways we can think about this using thermodynamics. Here's one of them. So when we're looking at our thermodynamics explanation, it comes back to our Gibbs free energy. So here's a expression showing Gibbs involving an enthalpy change and an entropy change for the system. Now we have considered what the sign of the Gibbs free energy tells us. If the sign is negative, we're talking about a spontaneous change. Two different ways I can get to, two different things that I can see within that. One is I can have a spontaneous change that will always be spontaneous if the reaction is exothermic and the entropy for the system is increasing. When those conditions are met, temperature is not an important factor. That will always be spontaneous. Now, the reverse of that, something that would never be spontaneous, would be an endothermic process where the entropy of the system is going down. That would never be spontaneous. The reverse would, but this would never be spontaneous. Now, if we're seeing something here where it says an endothermic reaction and a change in temperature, and we see this shifting taking place, it's telling me that the temperature dependence is important. We have a scenario in which it's an exothermic reaction, but the entropy change for the system is decreasing. In this case, the temperature is going to be important. It's exothermic, which means the entropy of the surroundings is increasing. Heat's going into the surroundings. But that's being balanced by the fact that the entropy of the system is going down. Flip of that would be something where it is an endothermic reaction. The entropy of the surroundings is decreasing, but the entropy of the system is increasing. In both of these cases, the temperature is going to be important. This idea on the endothermic example, because that's the one we're exploring here, this is more favored, more spontaneous, a larger K value when the temperature that we have this takes place at is large, because the entropy cost, the entropy change for the surroundings is going to be smaller. Our entropy is defined as the heat transferred reversibly over the temperature, and if we find the case if the temperature here is larger and larger for the same amount of heat being transferred, the entropy change is less. And since we're looking at the overall entropy change, if it is a process that is an endothermic one, we find that it is more favored when the temperature is higher.